Thank you. Hello, everyone. Although I couldn't attend this conference in person, but still great to have this opportunity to present online. So, yeah, so for this talk, it's a collaboration with my colleague at HEC Montreal, Eric Deloche. He's a professor at HEC Montreal, and then also with our PhD student who already graduated, Saeed Masban. And this project or this research is also a joint work with our industrial partner. There's Jeremy and Carl, so from the company Evervest. So this is like an internship project for our PhD students, and yeah. So but this work has been submitted to a journal. So it's good to have this opportunity to present this work here. Yeah, so the problem that we're considering is a portfolio management problem. It's basically a multi-stage portfolio management problem. And the setup we consider is that we have M, number of the risky assets in the market. And we have the decision to make, which is the proportion of wealth we're going to invest in each of the different assets. So that's why it's sum up to equal to 1. And we are have a decision on how to rebalance our portfolio at the beginning of every period from at different time point from T0 to T-1. And at every time point when we rebalance the portfolio, then there will be transaction cost incurred, and the exact amount depending on the size of our decision. And yeah, so starting at every time period T, then we denote the portfolio value and weight. It's a P-T-1 and W-T-1. And simple calculation will show us that if we want to calculate the end of period portfolio value, which is the value after the change of the stock market, the stock price, then we can calculate that by the initial stock price multiplied by the rate of return, and that give me the new portfolio value. And we can also then update our weight factor by normalize the value by the update end of period portfolio value. Okay. So this is how the transaction cost is calculated. So we have the new value minus the original value, and then if the value is getting larger, then which means that there's a transaction amount, and that transaction amount multiplied by the commission rate, and that give us the commission because of selling, and this give us the commission. Sorry, that's the transaction cost, not commission. The transaction cost based on the buying. Okay, so this is the we consider the possibility that the transaction cost rate might be different between the selling and purchasing. Yeah, and and then when it comes to calculating the transaction cost, although I don't detail this here because we have a limited amount of time, so I'm not good. I will not spend too much time on this formality of the mathematical detail, but basically, we can solve a equation in order to figure out based on the previous decision, the previous weight portfolio weight vector, and then the new one, and what will be the net effect of transaction cost on portfolio value, which we don't know by new T here. And with this, and with all the reason why we get through all this detail, just to say that finally, we can express the portfolio loss return at next period, which is by definition is the log of the ratio of the new value divided by the original value PT, and then that can be boiled down to the summation of the log of the the log of the net effect because of transaction cost, and also the log of the return, the portfolio return. Okay. And this kind of give you a summary of our problems formulation. At every time, at the beginning of every period T, we starting from with a PT minus 1 is our portfolio value, and WPT minus 1 is the beginning weight, the wealth distribution across different assets. And then because of the stock price that can be changing during the period time T, that will be leading to a new portfolio value, and then that according that will be have a new distribution of the wealth vector, because we will normalize by the new value during the given the change of the stock price. And then you will right before the next period, then we will decide whether or not we're going to rebalance the portfolio. And then if we rebalance, then it is a transaction cost will be incurred during this transaction during this time T, and the same cycle will be repeated throughout the process. Okay. All right, so that is a very brief and quick summary of the problem that we we're trying to solve. And really our goal to solve this problem is to explore the use of deep reinforcement learning to solve this dynamic decision problems. And as you know, some of you may be already familiar with this this type of problem, and knowing that when it comes to large scale or let's say multiple asset setting, then the issue of curse of dimensionality and the transaction cost, all of this just make the traditional method of dynamic programming doesn't work. But before we get into showing how we will be exploring the use of deep reinforcement learning to solve the problem, we will still starting from the formulation based on the Markov decision process, which is a common starting point when we try to solve a problem using deep reinforcement learning. So this is again, this is more for like for the notational convenience, you know, to make it consistent with how people work in reinforcement learning present work. So from the problem description that the mathematical model that we just speak about, we will recast everything in terms of the elements of Markov decision process, and the action obviously would be our wealth distribution vector WT. So which means that our action space is a continuous space, and this decision we make after we are observing the state in the market. Now the state in our problems is a high dimensional vector space, because we essentially considering the state could be a time window for the historical market observation, which including in our example, which including the latest stock returns, and also because we are dealing with transaction cost, so we also need to consider include the final portfolio composition of the previous period as the also as part of the state vector, right? So that's the way we carry the information about the previous investment or the previous decision, and then when we make a new decision, then that is needed in order to calculate the transaction cost, right? So we don't. Oh, okay. So this
Hi, this is Tarun. On your transaction cost, could you tell a little more about how you go about actually calculating? Is it just the commissions, or do you have some non-linear term to try and capture the market impact as well?
Oh, we didn't really go in detail in terms of the transaction cost. Really based on the fixed commission rate, and the cost is really like the larger the size of your the change of portfolio value. So let's say if you sell like $100 of the stock, then based on that size, you multiply by the commission rate, and that is the way we calculate the transaction cost. But we didn't consider the case, for example, if you making a much larger transaction, the impact of the final value that we haven't yet modeled.
Okay, thank you.
Yeah. Okay. Yeah. Okay. So for the state, it is essentially what we consider the state is a high-dimensional time series and multi-asset. So for each asset, for example, later you will see in the experiment, we considering both the open or close and the highest price throughout the day, well, actually at one point the students tried to incorporate about 10 different technical indicator for the state. So all this to say is that we try to go with a very general way of modeling the state, which is obviously different from the traditional dynamic programming, which can hardly be solved if the dimension go up to more than, let's say, 5 or 10, right? So here because we'll be relying largely on the deep reinforcement learning to solve a problem, so we do not really limit ourselves in terms of what can go into the state. And so for the immediate stochastic reward based on the current state and the action that made after observing the state and the new state, then basically that is for our problem setting, that is essentially it's the log of the change of value because of the transaction cost, which is here you can see that is this is where the previous portfolio composition and the new one that will come into play, right? So that's that, and that previous portfolio composition is included in the state vector. So and this is in the previous state vector, and this decision is our current action, and based on the decision that we include the transaction cost, and then this is the rate of return, and this is determined by either the latest stock return, but moreover that is also correlated. This is also correlated with other historical market information that that could be helpful for the prediction reason. So, and we have a transition probability that's just defined based on the classical definition. Okay. Oops. All right, and the objective that we try to solve. So with this kind of basic setup for the market decision process, then the last piece of elements that we need to define will be the objective, and the problems. For this MDP, we are trying to find the deterministic trading policy, mu theta. So we know that for deterministic policy in the MDP, it essentially is a function mapping the state to the action. So that would be the our mu. And we're dealing with extremely high dimensional problems, so we will need to bypass challenge by parameterize this policy function, and that's why I write the theta, mu theta. And later, really the focus is on parameterize this trading policy using the neural network, and then of course there's some more details on that, right? So this is our policy, and then we want to find a theta parameter so that you will maximize this objective function. Now, for this objective function that we try to maximize, we are considering a somehow relatively special criteria. It is the Sharpe ratio, but it's a simple trajectory based Sharpe ratio. So what that means is that the objective function is the expected value that will be taking over many different trajectory across the time, And for each trajectory, which is denoted by r from 0 to t-1, then we calculate the sample mean over that trajectory, divide by the sample standard deviation, and that is kind of like the Sharpe ratio based on that part one trajectory. And we have many different possible trajectories, so we calculate the expectation of the sample Sharpe ratio. And our goal is to find a policy that so that when you make the decision according to that policy, this average of the sample Sharpe ratio can be maximized. Okay, so the reason why I mentioned that this is kind of different from the some other criteria is because, first of all, this is like a trajectory-based average, and for this kind of objective function, it is basically not possible to solve by the dynamic programming principle, which is like Bellman equation, because this objective function does not have this kind of recursive structure, which is usually needed for the use of Bellman equation. However, from the reinforcement learning perspective, if you look at this problem, this is nothing more than just a sample average. And by knowing that this is just a simple average, and then this essentially is just the summation across many different trajectory statistics, what we can do is just simply use the stochastic gradient descent to solve the problem. So we can update the parameter for our decision policy by the stochastic gradient descent, and which means that for each trajectory that we sample, we will just update the theta from by taking the learning rate alpha multiplied by the gradient of the Sharpe ratio function that we define based on that trajectory path. So of course we will have different number of trajectory. Every time we have different trajectory paths, then we just update the sample by sample. And in terms of calculating the gradient for the trajectory for the Sharpe ratio function, for every trajectory, then it can be done by the back propagation using the chain rule, just like what we usually do for deep learning. Okay, so this kind of formulation setup is more it can kind of be classified as an actor-only method in reinforcement learning. First of all, like I said, the object function is not really following the scope of traditional dynamic programming. It's not recursive. So really the way we solve it is like we parameterize the policy function and then just solve it as if it is a sample average expectation problem. And this is kind of the more of the approach similar to the actor-only method in the reinforcement learning. You know, we have some other follow-up work where we formulate object function differently, and which involving measuring the risk in a recursive fashion. Then in that case, we have this kind of Bellman type of recursive equation. Then that's where we can further solve the problem using this kind of actor critique method in reinforcement learning. Okay, but for this talk, I'm going to focus on this setup, and then this is partially motivated by the interest for our industry partner, thinking that this is like seems to be practically relatively straightforward criteria to be considered. Okay. Yeah. Oh, okay. So I think in the interest of time, I think I only have about 5 or 10 minutes left. Okay. So really, the challenge that we are facing is that the policy network mu theta is a high dimensional function, and we put lots of effort in designing a neural network that fit this application. And there are a few principles behind the way we design this policy neural network. First of all, the neural network should be able to handle the long time historic time series, and because we want to extract the long-term dependency information across time. And secondly, the network should be flexible enough to capture the dependency across different assets. And thirdly, the network should be parsimoniously parameterized, because we know that in reinforcement learning, the overfitting is a serious issue, right? We know that reinforcement learning compares deep reinforcement learning compared to the deep learning to some extent is a much harder problem in that it need much more data in order to have a good performance. So if without having enough of data, then the network should be designed in a more parsimonious fashion, so that to avoid the overfitting issue. So the base structure that we employed is called a WaveNet structure, which is very which has received lots of attention back in 2016, and I think there's lots of follow-up work. Essentially, it is the use of a convolutional network, but it's a little bit slightly a more advanced variant of the convolutional neural network to handle the time series data. So the WaveNet, they can capture the cross-asset correlation information, but the problem is that it is hard to sorry. So the WaveNet basically is the best to capture the dependency information across time. But one special feature of this formula management problem is that we want to capture the cross-asset correlation information. So if we want to extend the WaveNet structure, which is best suited for the case of capturing the dependency across time to the multi-dimensional, to multi-asset case, then either it can, a straightforward extension can either easily leading to a huge number of the parameter and leading to the issue of overfitting, or it can just be leading to a kind of strange solution, and which is the issue that we notice, which is that the network will turn to be sensitive to the way we input the state data. So in particular, what we notice is that if you have the same time series, and then each you have the same time series across asset, but just permuting the time series in the asset in terms of asset index, then the result can be very different. And the reason for that is because it is this WaveNet structure is a parsimoniously designed convolutional neural network, but it is not really permutation invariant, meaning that if you permute your time series data, if you permute the asset index in the time series data, then your final solution can be very different. On the other hand, to give you an example of in which case this the neural network will be permutation invariant, then that will be, let's say, the simplest fully connected neural network. In the simplest fully connected neural network, even if you permute your time series data in the asset dimension, then the resulting predicted decision, which is in our case, which is the Wells allocation vector, was simply to be the permute version of the original Wells vector. But although the simplest fully connected neural network would not have this permutation, would not have this issue that's being sensitive to permutation, but at the same time, it is an overly parameterized neural network, right? So, and that would not be, so really how to find the balance, or how to find a way to design a neural network that is parsimoniously designed, meaning that there's not too many parameters, but at the same time, it would not be sensitive to the permutation of the ordering in the time series data. That is really what we put effort into figuring out into fixing this issue. So I don't think I will have time to go through the details of the neural network, the network structure, but just to show you that we have the market data, which is a tensor, which is the m-dimensional, which is m many asset and h many time period, and then d many different features such as high price, low price, closing price, so different feature. And this is our input of the Wells allocation decision, and this is altogether is our state, and then that will be passing through this wave correlation block, which will be capturing the both the cross asset and cross time dependency information, and eventually that will be passing through the softmax and to give us the decision to make. Okay, so that is kind of the general structure, the general policy general structure for all policy neural network. And yeah, so this is something I just mentioned. We define more formally this property of permutation invariance just because we noticed that the straightforward extension of this WaveNet actually does not satisfy this permutation invariance property, and leading to lots of concern for our industry partner, because it does not make sense just by permuting the data. You will have a very different decision. That is what is concerning. So for each of the wave correlation block, it is taking this structure. So basically, you can see this layer of a dilated convolution network and passing through the red rule, and then etc. So this is more like following closely the structure of the WaveNet. But really, what's the special part of this network that we design is this correlation layer. So this correlation layer is where that we take the multi-asset input and then trying to mapping to a new vector, so that each entry will be capturing the cross-asset information, right? So because remember that the output, you can think of that output is our decision of how much to invest, the percentage of weight, the percentage of wealth that we invest in each different asset. And we want every decision or every percent decision over for each asset, depending across the information, depending on the information that across asset, right? So which means that every output of the decision should be as a function of all the data across the different asset. And that's what the correlation layer is doing. And so here is the way we design the correlation layer. This is the previous one. So
sorry, Jonathan. We are. Do you want to conclude in a couple of minutes? We are already.
Yeah, we are. Oh, sorry. Yeah, sorry. It's this.
Sure.
Yeah. Okay. So So anyway, I hope that I already give you some of enough sense that really the major issue that we're dealing with is to figure out how to design a neural network so that it will not be sensitive to this permutation issue, but at the same time it can have the benefit of the convolution network. So I want to just mention using the last few minutes about our experimental result. So we run our new neural network architecture using the Canada data and the US data and the COVID data. So what I mean by COVID is that we train the model using the pre-COVID data, and then we test the model using data from COVID, just to stress test how reliable, how good the model is. And we compare our performance with a few other models. And so I don't think I will go through the details of the number, but basically, the long story short, our observations that our model, which embraced the benefit of both the convolution network at the same time to be permutation invariant, and it turns out that the performance is really consistently outperform the other benchmark across the board. And for Canada, US data, and COVID data. And interestingly, doing it for the COVID data, you actually outperform most obviously. And this is some demonstration about the sensitivity to permutation. So you can see that for the other paper that have a straightforward extension or naive extension of the WaveNet, just by permuting the way you input the data, the result can be vary significantly. And in our case, we have very small variation, but this is mostly because the nature of the random, starting random seed in the neural network. So that can degree of variation, but it is by no means as sensitive as the naive extension of the WaveNet neural network. So in summary, basically what I just presented to you is one of our attempt to borrow one of the latest deep neural network architecture, but then we came across this issue that the network can be sensitive to the way the data is inputted, and then we kind of figure a way out to redesign this the kernel. Well, in the convolution network, it's called the kernel. We redesigned the kernel so that it will satisfy this permutation invariant property. And then this overall, we test this on an extensive set of real life data, and then this has been, I think this is much more acceptable to our industry partner, and that's kind of the brief summary of my research. So thank you for your attention.